Hi, ladies and gentlemen. Our next part of modern physics is regarding atomic energy levels, which was a theory proposed by Bohr, especially when you guys were talking about the Bohr model of the atom. We had previously determined that a photon is able to knock an electron out. This is during the photoelectric effect. And the electron takes the energy of the photon and uses it to escape. But electrons don't always escape, but they can still take the energy of the light. In fact, they're able to go to a higher energy state and then drop back down, which is what we're going to be talking about today. In chemistry, you guys probably had done something similar to a flame test, right? When you guys did a flame test, you guys then looked at the flame through a spectroscope. But the interesting thing was, when you looked through the spectroscope at the gas, right? When you looked through the spectroscope at the gas, you would only see a series of discrete lines. You wouldn't see a continuous band like you might expect to, especially if the color of the light seems like it's going to be bright enough that's almost white light. The same thing happens if you take dish spectrum tubes, where they excite the gases inside these tubes. In this case, we have helium gas. And if you do the same thing, and over here now we have neon gas. And when you look through the spectroscope at these gases, you end up seeing very discrete lines. Now that confused scientists, because scientists had expected to see a continuous band of light, especially if it's from white light. But instead, they saw, especially with hydrogen, they saw 4 very specific bands of light: purple, blue, green, and red. So Niels Bohr took this to mean that, well, probably these electrons must exist at very specific energy levels. And these were the orbits of the electrons. Okay? And he theorized that those electrons could jump up and down between the different orbits, similar to if you were to say a marble going up and down a set of stairs. So in one case, this would be the lowest orbit, or he called it ground state. And it took a specific amount of energy to get it from one step to next step to next step. And these steps weren't all even, but it could only exist at those different steps. In other words, if it took, let's say, 10.2 electron volts to get to the second step, if the electron didn't get 10.2 electron volts exactly, it wouldn't jump. Okay? The fact is, it will only receive the exact amount of energy would it be able to make it up to the next step. And that's where these bands of light come into play. Because when we go back to this animation over here, when we see these different bands of light, he took this information to be, well, those bands of light are specifically the exact energy amounts between the different orbits. And when the electron jumped up to a higher orbit and then jumped back down, it would give off certain colors of light. Okay, so jumping up, whenever the electron absorbs energy, and it jumps back down whenever the electron emits energy. And this energy, of course, will be emitted in the form of light. And the amount of energy that emitted will, of course, correspond with the color of light based on the formula E is equal to HF. So we can see that the higher jumps the bigger jumps gave off more energy, they would give off energy that's closest with the smaller wavelengths. Okay, and this over here is just another example of the same thing, where you have the different energy levels, and you can see the first orbit, second, third, fourth, fifth orbit over here, and since each jump, notice it does not have to jump one step at a time, the electrons can jump multiple steps at a time, whether it's going up or going down. And the bigger the jump, the more energy there is, which is why if you take a look at these four jumps over here, this jump has the highest energy, which is why it's purple, because purple has the highest frequency. This jump has the lowest energy, and that makes it yellow. Okay. Of course, these jumps over here are even less energy, which is why they end up looking like they're going to be red instead. Because according to Roy G. Biv, red is the lowest energy, violet is the highest energy. Now, rather than, of course, drawing it in terms of always drawing orbits and drawing circles, Niels Bohr instead made it look like a ladder instead. So that way you could jump up and down the different rungs of the ladder. And in your regions reference table, you have these two energy level diagrams, one for hydrogen and one for mercury. And you can see the different orbits over here, 1 through 6. Notice there's an infinity symbol at the top. We'll talk about that in a moment. That's the ionization level. Okay, and over here on the right side, we have the corresponding energy values of each level. So the first level is worth negative 13.6. The second level is worth negative 3.4. So in order for an electron to jump from the first state to the second state, it must receive enough energy to jump. So in this case, if light came in, that had an energy of 10.2 electron volts, I got that by subtracting 13.6 and 3.4, then the electron would jump up. After the electron's up on the top, it of course always has the option to jump back down. And when it jumps down, releasing its energy, we'll see that it'll actually give off the same amount of energy that absorbed in the first place. But let's actually take a look at this animation over here, just so we can discuss what happens at different levels. All right, in this example over here, we have an electron orbiting at the very first level. If I send in a photon now, it absorbed the photon and went to a higher level. But afterwards, of course, it wants to jump back down, and it was then emitted. And notice that the energy of the photon over here in the bottom right was about 10.2 electron volts. Okay. Now, what's more interesting though is if it absorbs a larger one. In this case, it's at the third level. It could jump all the way back down, but doesn't have to jump all the way back down right away. It could just jump one at a time. Okay, so if we go back to this diagram over here, if an electron absorbed enough energy to jump to the third level, okay, so how much energy will it need to absorb? Well, you take 13.6, 1.51. The energy here would equal to 12.09 electron volts. Okay, so if it absorbed 12.09 electron volts exactly, it would jump all the way up to the third level. If it's not the exact amount, it won't jump at all. But when it's at the third level, it has several options. If it wanted to, it could jump all the way back down. Or it could take its time and jump from one step to the next. So there are actually three different possible colors of light being given off over here. It could give off the 12.09 electron volts again, or if it jumps from 3 to 2, it would give off, when you subtract those two numbers, it would give off 1.89 electron volts. And then when it jumped from 2 to 1, it would give off 10.2 electron volts. Okay? So there's three different possible colors being given off in this case. Of course, how would we actually solve for what the color is? Well, we can always solve for the wavelength by setting any of these values equal to hc over lambda. Okay, so lambda in this case would just equal to 1240 EV/nm divided by 12.09 electron volts. So the first one ends up being 102.56 nanometers. Now this would actually not be visible to us. This is actually ultraviolet light. So ultimately, if it jumps all the way to the top level, in this case, the fourth level, it could jump all the way back down to the first. It could jump 4 to 3, 3 to 2, 2 to 1. It could jump 4 to 2, 2 to 1. In other words, there's lots of options it could take. There's lots of different colors that could be given off in each jump. Okay? Now, it must be noted, of course, that Bohr's model didn't always work. In fact, it worked best for hydrogen and for mercury. For everything else, it didn't quite work out. The energy levels didn't always seem to make sense. Now, part of the reason for that is because electrons don't actually orbit the atom. Well, I guess you could say that they kind of do, but we had previously stated that an electron, because it's so tiny, has both particle properties and wave properties. So because it has both wave properties, it's actually acting as a standing wave around the atom, around the nucleus itself. Okay, and what this picture over here is just trying to show you is all the forms of the standing waves that it could take. But let me show you this picture instead. You see, we're used to seeing standing waves in a line. In this case over here, we have our nodes and our antinodes. We have 1, 2, 3, 4, 5 nodes and 4 nodes. And we could change it up to be larger or smaller depending on whatever values we set for it. Okay? And you just have to imagine those standing waves and now just connect them all the way around in a circle. Okay? Doesn't matter how many there are, but the fact is the higher the energy, really, the more higher the frequency, the greater the standing wave. Okay? So if you imagine connecting it around in a circle, when we take a look at this point over here, we can see that over here there are 3 standing waves here, 4, 5, and 6. And these actually would correspond with the different energy levels. N equals 3, N equals 4, N equals 5, and N equals 6. So when the electrons are actually absorbing the energy, they're not really jumping up to a high energy level because there are no such thing as orbits. Rather, what they're doing is they're turning into a different type of standing wave that's vibrating as it goes around the nucleus. Okay? So that's what de Broglie was really talking about, how electrons are able to act as waves, and they actually act as a standing wave as they vibrate around the nucleus itself. But for our purposes, for the exam, we're going to think about in terms of energy levels as rungs on a ladder, just because it's a little bit easier to visualize. And 2 key words to remember here are, of course, ground state, which is the lowest energy state. And we're right here, actually, ionization energy. Okay, ionization energy means the electron receives enough energy to escape the atom. In fact, it becomes an ion, which is what you learned last year in chemistry. When an atom becomes positively charged or negatively charged, it's about an electron escaping or being gained. So if something becomes a positive ion, it's when an electron actually escapes. Now, if an electron actually receives more than enough energy to ionize, this is the one time where I had normally said before that you need exact amount of energy to jump up and down between the different energy levels. But if you receive more than enough energy to ionize, the electron still manages to escape, and the extra energy becomes kinetic energy. In fact, this is almost exactly like the photoelectric effect again, where the work function was how much energy the electron needed to escape, and any extra energy left over became kinetic energy. So if you go back to our chart over here, okay, so as one example, let's say there's an electron in the second level of hydrogen, and light shines onto it with an energy of 5 electron volts. Okay. Now that's more than enough energy to reach the top. So the electron is still going to jump. It reaches the top, and it uses up 3.4 to 0. It's 3.4. It uses up 3.4 electron volts to jump up and escape, to ionize. So the electron now at this point shoots off and has a certain kinetic energy, which is equal to the energy of the photon, 5.5, minus the energy needed to escape, minus 3.4, which equals to 2.1 electron volts. Okay, so it's very similar to the photoelectric effect, where the extra energy left over becomes the kinetic energy of the electron itself.